Hai guys. Halo.
Halo Kak.
Tadi Pak Dev-nya sudah masuk untuk pelatihan belum ya?
Sudah Kak.
Oh sudah, oke, good.
Halo, halo. Sania. Halo, halo. Yes, tes. Suara gue jelas gak, Sania? Hello everyone. I'll start the webinar ya. Ladies and gentlemen, welcome to the ICE technical meeting, Percussion-Driven Earth Anchoring System Introduction with a selection of case studies from Australia. This event is brought to you by the Institution of Civil Engineers. My name is Marvin Bennett from ICE Student Chapter University, and it is a pleasure to act as your master ceremony in this event. Before we start, allow me to read the rundown of our events this evening. First, I will be reading the rules of the webinar. Second, there will be opening remarks by Phil Woodmansey, followed by an introduction by our moderator, Michael Duby, to start the presentation of our speaker, Dave Markham, this evening. The event will then continue with a Q&A session. Ladies and gentlemen, for your own convenience, please pay attention to the following rules. You can ask your questions to the speaker by pressing the raise hand feature located at the bottom of the screen. The question should be in English. You can raise your question after the presentation of the speaker. You can also raise your question from the Q&A feature located at the bottom of the screen if you prefer the moderator to read your questions. Now, I would like to invite Phil Woodmansey to give his opening remarks. To Phil Woodmansey, the time is yours.
Okay, thanks, Malvin. Apologies, everyone, if you can hear the sirens. I am right in the middle of the city and there's something going on outside, but I hope you can hear me okay. Welcome, everyone, to our ICE Jakarta Local Association technical presentation. For those of you who know, we try to run good quality presentations once a month or thereabouts. Normally, we're live at our home location at the Eastern Promise in Kemang, but tonight we're completely remote again because our speaker, Dave Markham, is based in Australia, where it's getting quite late there. And so thank you, Dave, for taking the time to talk to us. I think on that note, I'll allow Mike to introduce you and look forward to listening to your presentation.
Hey, thanks very much, Phil. So I have the pleasure this evening of introducing our speaker and the topic which he's going to speak about. So Dave Markham is a civil engineer who started his career in the UK. But he moved out in this direction, I think, quite a few years ago, lives in Australia these days. And he's worked in a number of areas there. But I first met Dave when he was working with a geosynthetics company associated with the work that we do there. And in fact, it's quite nice to actually welcome Dave back to Indonesia this evening, but unfortunately in only a virtual way, Dave. It's a shame you're not actually here in the Eastern Promise pub, but never mind. Maybe that can happen on the next occasion. I think in your more recent endeavors in Australia, you have started a company by the name of Retaining Technologies Group Pty Limited, and I think we're probably going to hear a little bit about some of the background to this company in a few minutes. But I think as possibly some people know, it's also a field that I get involved in retaining walls and similar things. But today we're going to hear about something a little bit different. I'm used to reinforced soil, where we build fills and we can bury reinforcement within the fill, but we often get problems where we have soil masses that are themselves maybe unstable, or we have problems with them, but it's inconvenient to remove them, or we can't remove them, and we need to try and deal with the problem in a different way. And I'm thinking that's probably what we're going to hear about tonight from Dave. He's going to talk about what are now called percussion-driven earth anchoring systems. I happen to know, we know already, there's going to be some very nice explanation as to exactly what these techniques consist of. I'm looking forward to hearing about that, Dave, and also to hearing about some case studies from Australia, where you've been involved in putting these techniques into action to solve problems. And I think that's what we're really interested in. I think you're going to learn that In Australia, there's been some extreme weather over the last couple of years or so, and this has certainly aggravated a lot of geotechnical situations and created stability problems. Well, I guess this is something, a situation where we're looking for technologies that offer something different or new, something efficient and cost effective. And I think, Dave, I'd like just to invite you now to make your presentation on behalf of the ICE in Jakarta. Thank you very much for taking the time out of your evening to talk to us. I said, I'm sorry you can't be here and share a refreshment in the Eastern Promise pub, but we'll do that next time. So Phil's name is up here. Sorry, Dave, you're now free to talk to us about this very interesting topic. Thanks very much.
Okay, you can hear me, Mike, yeah?
Yes, very clearly,
yeah.
Yep.
Loud and clear, excellent.
Yep.
Well, thank you very much for the introduction. Before I share my presentation, just good evening to everyone from here in Australia, in Brisbane. First of all, I'd like to thank you very much for inviting me along this evening to present an overview of this percussion-driven earth anchoring system. I want to share with you this evening some of the basic principles of using this type of system, but to also give you an idea of where it's been used here in Australia over the last 7 years. I've found it quite a smart, clever anchoring system and solution, which may not be the answer to all your engineering problems and challenges, but when it can be used, it is invariably an attractive, cost-effective, and sustainable option for you to consider in your projects. So I'm just going to share my screen now, hopefully.
Yep, it's coming through nicely, Dave. Fantastic.
Oh, good. Okay. Just a very brief introduction to the company that I work for and I run here in Australia. As Mike said, it's quite a young company, but it's called Retaining Technologies Group, and it delivers turnkey type solutions or total solutions. And what that does is it brings together all the engineering, the products and systems needed to solve embankment stability and retaining wall problems, and also the installation. And equally as important is the supervision and management of these projects to make sure that they're built to a high quality, to make sure they're built safely, and to also make sure that they meet a client's budget expectations. Okay. So let's dive straight into the main topic of discussion tonight, which is the percussion-driven earth anchoring system. So there's a couple of photos on this slide. These are actually both temporary works projects using this type of system. The one above the text is actually quite a new or relatively new project that was carried out at a place called Deception Bay in Queensland. And it's a temporary works application. You can see it's a very steep slope, up to, I think it was 9 meters in height. And it's stabilizing that embankment using this anchor system to allow a new bridge abutment to be built in front of it. Okay. Right, so I'm going to give you a bit of an overview of this system and where it's come from. I also want to talk about how the system functions, how it works from a load locking and bearing capacity application. And then we'll go on and talk a little bit about applications and where this system's being used in temporary works, remedial measure works, and finally permanent work solutions. So I'm referring to this as a percussion-driven earth anchor system. Sometimes it can be referred to as a mechanical deadman anchor system. So let's understand a little bit about what deadman anchors are. There's certainly nothing new. They've been around for centuries, guys and girls. Certainly I know for a fact Romans and the Egyptian periods used this type of concept of burying something in the soil to provide an anchor as such, or to be able to put a tension force on it. Where the percussion-driven earth anchor system differs, and it's been around for now commercially probably 30, if not 40 years, What you do with this system is you drive it into the soil, and you drive it to whatever depth you need. You then tension it such that the anchor flips in the soil and becomes a dead man. Okay, so it's a percussion-driven earth anchor. And I think at this point, I should mention that word earth, because it is very much an earth anchor solution. It's not a rock bolt. So you've got to be using this system in displaceable soils, material that you can actually displace. So it's not a rock anchor. So this is not the right solution for hard, sandstones or maybe granites. This is very much an earth anchor option. As a system, it can be rapidly deployed and can be corrosive resistant. And, installing it, you can use traditional or conventional portable equipment, from the smallest equipment like a manual, maybe sledgehammer, knocking a drive rod in, to maybe a small jackhammer to put smaller anchors in, to the other end of the spectrum where you use a small excavator, typically 5 to 8 tons in capacity, with a mounted breaker, a percussion mounted breaker that drives the anchor into the soil. Now, one of the clever things about the system is that you get your load immediately. So you drive your anchor in, you determine your load almost immediately, the holding capacity. So that's a big benefit over, for example, say a traditional drilled and grouted solution, where once you've grouted, you've got to wait, several days for the grout to go off, and then you can only then test the anchor. So you've got this instant load verification with this dry system. Give you some idea of the sort of loads to expect from it, and this is, for some of your jobs and projects to solve problems on. Typically, with this type of solution, in my opinion, up to ultimate loads of maybe 200 kilonewtons, that's 20 tons. So once you then start to add your factors of safety in and bring it back, you're working in design loads for this system. Typically, I would say as low as maybe half a ton or 5 kilonewtons, up to maybe 10 tons, possibly 12 tons. So that's 120 kilonewtons. So you can actually solve quite a lot of engineering challenges or problems with that load range. And of course, if you need something a bit, stronger and more tensile strength than that, you'd be looking at maybe another system, maybe a very large drilled and grouted, or possibly even a screw anchor. So we refer to this solution as a system, and I'm just going to see if I can get a pointer here. Yeah. So we've got to look at the whole thing as a system. So when you're designing and detailing it, don't just think of the anchor head, think of all the other components. And there's very much 5 components to the whole anchor system. So you've got your head, you've then got some sort of lower termination that connects the wire, tendon, or maybe a rigid rod to the anchor head. And then at the top here, your top accessory, your top termination, could be a load plate, could be a wedge grip, or maybe a nut of sorts. But always think of this as a system. Giving you some idea of the sort of load plate arrangements. Here you've got a selection of applications. Certainly the top right there, you've got remedial works to maybe an existing wall. Down the bottom there, you've got the anchoring system holding back an erosion type control matting. And then in the top left there, that could possibly be a gabion, which is either incorporated in the permanent works or maybe installed afterwards as a retrofit for some remedial works. These are just a few photos. I was quite fortunate just before COVID, a couple of years ago, to go to Switzerland and to walk some sites with a contractor there that does an extensive amount of this type of solution using this type of system for embankment slope stability. The ground, if you've ever been to Switzerland, is very undulating. The ground conditions are pretty ideal for using and deploying this type of system. But I picked up quite a lot of information on how they go about their business and their adopting their type of solutions with it. And I really quite liked, in this top left-hand corner here, the whaling plate arrangement. And this is very much for a temporary embankment here. But they come up with these channel sections, which I thought were quite clever to spread the load out over the slope. You can see the mesh in the face there and an erosion map as well. And also they're very clever with their quality assurance. You can see those little tags on there. Actually, every anchor they install is numbered, and then they relate that back to a quality assurance program or quality assurance sheet to give confidence to all stakeholders that these anchors are being put in correctly to whatever depth and whatever load that they need. So let's have a look a little bit at the applications of this percussion-driven earth anchor. So towards the left here, very much civil engineering, very much slope stability. You can see in the top left there a remedial measure for maybe an existing wall. So the wall may be showing signs of moving, possibly failing. Not necessarily you don't want to take it down, we want to just extend the life of it. So this system can potentially be used for remedial measures. Then as we move around these sort of images, we move to more a holding down mechanism. So we've got embankment stability with this system, but then we've got this holding down as well. So here we've got tree anchoring, we've got pipeline buoyancy, and certainly I know up in Europe, the utilities these anchors use to hold down maybe power lines or possibly telecom lines, they're used pretty extensively for both temporary and permanent works applications. Just another similar, I suppose, drawing or image showing the endless applications of where you can potentially use this to solve problems. As we come towards the end of the presentation a bit later, you'll get to see some of those endless applications where you can use this type of solution to hold down things and to provide embankment stability. Okay, so let's go on and talk a little about the load locking and the bearing capacity, if I can. So this slide shows us the variables. Okay, you want to get an idea of what sort of load you're going to get with your anchoring system. So let's have a look at the mechanical performance and the various variables that give it, the load that you can get out of it. So first is the bearing capacity of the ground, and certainly higher friction soils like sands and gravels, you arguably will get better loads, okay? One of the other variables is pretty obvious, which is the anchor head size. And I'm sure one of your questions could well be, well, what sort of size anchors, heads do we have? And I would say probably the smallest ones might be something like 75 mil, 3 inches in Old Bay, up to maybe a ½ meter, if not a meter in size. So that's 1,000 millimeters. So we can have some pretty big anchor heads. And the limit is on whether you can actually get them into the ground with the equipment that you've got, okay? With friction soils, there is another variable that gives you the load on the anchor, and that's the overburden depth to the anchor head, okay? That's only with friction soils, but that will have a bearing on what sort of load you will get out of your system. Then, of course, there's the strength of the tendon and bar. You mustn't forget that. It's all very well to put a head in the a head in the soil and say, right, that's good for 10 tons or whatever. But equally, then, if you need a design load of 10 tons, you need to make sure that your tendon will be able to give you 10 tons and give you it for a long period if it's a permanent works. So this is where your durability performance comes in, the materials you specify, and you've got to look carefully at the application and the exposure and the corrosion. What sort of soil types are you driving these into? Is it near maybe a river or possibly even a saline water environment, which will affect durability and corrosion? The photo on the right there is actually a job I was involved in Sydney some years back now. It's a temporary works project right on Sydney Harbour, but you can see the material in here is a very nice dense, medium dense sand, which gave ideal loadings for this temporary works retaining wall. You can see it's a contiguous piled wall, and then you've got 2 levels of anchors, lower level and higher level anchors. I think the loads we were getting out of this system was typically, I think it was 8 or 9 tons as a working design load. But they were ideal conditions to drive this anchor system into the ground. So let's have a look at how this system works in bearing stress failure. So here we have, say, for example, friction soils, sands and gravels. And what happens when you tension the anchor is you get this frustrum soil of resistance forming at the back. When you're designing with it, it's a bit like designing a footing, but turned upside down, if that makes sense. So you're pulling against the soil rather than pushing against the soil. So this is where you can use Tasagi in your design analysis. And you can see with the friction soils, you're getting quite a wide wedge or frustrum cone of soil resistance. If we have a look at cohesive soils now, and because you've got weaker soils here, we're ending up with a much slender cohesive or slender frustrum cone of resistance. Okay, so quite often it doesn't mean you can't use this system in cohesive soils, but what you may have to choose is maybe a larger head to give you that working load that you need, whereas maybe a smaller head in friction soils will do the job compared to, say, cohesive soils. What is really good with not just anchor installation, but also soil nails is to, wherever you can, do a trial. You know yourselves as engineers on jobs where you may have the best geotech or most extensive geotech investigation carried out. You could have numerous boreholes, site trial pits, possibly DCPs, but quite often you'll go and drive your anchor or soil nail, and the ground is unforeseen. You experience something completely different to what was actually in the trial pits or in the boreholes. So it's ideal if you can actually do a trial on a project. It's not always possible, but if you can, it is ideal. And then just in the middle photo here, this is some creep testing that we do in Australia under Australian standards for permanent works. It involves loading the anchor a number of cycles over a period of time and just measuring that deformation of the anchor if there's any creep. So it's quite a extensive test that can last probably a morning when you do the actual load testing. Let's have a look and see how now. So if you can imagine this anchor is now installed into the soil. Now let's tension it. I'm just going to let this run through. So now what I want to do is analyze each of these areas of load lock compaction, then reaching your bearing stress failure. So if we have a look at the first, once you've driven the anchor into the soil, you can see this is a graph that shows the load versus extension. When you first tension the anchor, you get quite a bit of extension, not very much load. And that's when the anchor is simply turning in the soil to become a dead man, yeah? Then it starts to compact and starts to take up load. But you can see you're starting to reduce the extension, but you're getting much more load. And then ultimately, if we pull it so hard and we reach the ultimate load, we get bearing stress failure. Now, as engineers on a job, we will ask of the system a design load or a working load. So what you do on every anchor that you install with this percussion-driven earth anchor is you proof load them. Every anchor gets proof loaded. And what that proof load tells you is it gives you the confidence you've reached your working or design load, but you're below your ultimate load. So you're not shearing the soil, and effectively the system's becoming a bit redundant. So the proof load is generally 10, 20% above the working load, but every anchor gets that verification. Right, let's start to talk about some projects if we can, and if we go straight into a temporary works project. But before I do, I want to show you this little animation. Hopefully it'll work for a cut face. So in Australia here, and maybe you do in Indonesia as well, from a safety point of view, if we're doing a temporary batter, quite often we'll do what we call a top-down construction. So we'll only excavate maybe a meter or a meter and a half, possibly 2 meters, and we drive the anchors into position. Okay, you can see now the excavator, as I said to you earlier, a typical 5-8 ton excavator, driving the anchors into whatever depth you need. We're now removing those drive rods, which are temporary, to get the anchor into position. But now we've already seen an erosion mat on the face because it's a steep face, maybe 60 or 70 degrees. We're loading those anchors up, stressing them. So they're now reaching their proof loads. Quite often in this application, the anchors are active and not passive, so they're under stress. So we carry on and do the first layer. And once that's stabilized, we then excavate out another 1.5 meters, 2 meters, place the anchors in, and so on and so on. That's quite a safe way of actually carrying out a temporary anchor solution with this type of system. I thought I'd show this image, girls and guys. About 3 or 4 years ago, this was drawn to my attention. It was a temporary works project, and it was a case of the contractor taking an element of risk. And you can quite often get it wrong if you do not do your risk assessment properly. And on this particular occasion, you can see this slope. It was a temporary slope, supported a railway at the top here. And we had a very extreme weather event. You can see it's quite wet in front of the wall anyway. Now, whether it was a combination of this particular shotcrete should have had anchors in, and also maybe the detailing where water got behind the shotcrete as a result of the failure. But, something that, you don't manage properly or design properly can cause you a lot of disruption, cause you a lot of money and time lost on the project. So the first job project I want to talk to you about today is called the M4 West Connex project. And the temporary works actually was carried out over probably a couple of years. So from an overview perspective, some of the key stakeholders on this project, this was in Sydney, by the way, was Leighton's, the contractor, which they're now referred to as CBP contractors here in Australia. They're a tier 1 contractor. And we've got reputable designers of Coffee and Smec involved as the consultants. The project, in essence, involves widening of the M4 motorway in Sydney, which is a very busy motorway near Sydney Airport, some 7.5 kilometres in length. And the works for the temporary works involved installing some 1,500 percussion-driven earth anchor systems, design loads of 6 tons, 60 kilonewtons, to stabilize a very steep 60-degree embankment up to maybe heights of 9 meters, okay? So let me just sort of highlight a few key features of using this system. And what I'm hoping you'll find from these short case studies is there's a common thread coming out, common message, and that's the constructability. How quick you can get this anchor system in and get it loaded. So there's a big constructible and buildability to this system if it can solve your problem. So you mustn't always look at just the supply cost of maybe materials. You've got to look at the whole job, the total cost, the resources needed to put them in and how quickly you can get them in. If you're interested in this particular project, there was a paper presented at the Australian Geotechnical Society in Sydney back in 2017. And if you want to drop me an email, I'd be more than happy to share that paper with yourselves. So this is just some preliminary analysis carried out using, I think it was slope, modeling these anchor systems. From this, you can see it's a steep batter. Okay, this particular section is up to maybe nearly 7 meters. The anchors are spaced on the face at 2 meters by 1.5 meters. And I think you can see that quite high surcharge loading from the M4 at the top there. Finish off this project with some images of the job being constructed. In the left-hand image, you've got a typical gang here driving those anchors into maybe 6 or 7 meters depth. So this is an excavator, I mentioned again, typically 5 to 8 tons with a breaker, percussion driving them in, and an operator. And then you've got a couple of operatives supporting the project. The image in the middle there is the typical facing. What the engineers used here is a combination type grid of geotextile and geogrid, bidirectional geogrid to transfer loads between the anchor heads in both directions. And he's actually added an additional strength of mesh in the lower layers because that's where the stresses are highest, probably from a belt and braces point of view. But I'd just like to stress the importance also of that geotextile that's built into that to provide that surface erosion for that very steep face. The worst thing that can happen is you get a heavy rainfall event, and if you've not got that protected, you can get into all sorts of problems with the face being washed away and erosion of the anchoring, where the anchors then start to lose their integrity. So that erosion of the steep face in the short term is very important. This one really sums up exactly what this photo on the right here, what the project's all about. That temporary batter, so you can see the M4 motorway at the top there, to allow a permanent MSE, mechanical stabilized earth wall, to be built in front of the wall, okay? I can't stress enough, I mean, the original solution on this job was sheet piles as a temporary work solution. There was concerns about driving the sheets into the depth required. There were concerns about taking the sheet piles out. There was also concerns about the noise factor. And of course, there was a cost. And from what I understand, we were looking at a saving of something like 20% overall on this job using this anchoring system. But a lovely thing about it is it could be turned on and turned off quite easily as and when they needed to do the temporary works. And they actually carried out the works themselves with a bit of training and support from the supplier. So give you some idea of installation. So those anchors were on the face at 2 meters by 1.5 meter. I know for a fact that a typical gang was putting in something like 25 and 30 anchors a day, load verified as well. So you can imagine just how much temporary works you can expose and just how quickly you can get that installed with using this type of system. Okay, let's move on now to a remedial works application using the percussion-driven earth anchor. I've got another little animation here for you. So here now we've got an existing wall, and we've cored a hole through that wall. And we're driving the anchors in a similar way as what we did previously with the temporary works, okay, using an excavator, using drive rods. Now, this remedial measure is not to push walls back into position. It is very much there to extend the life of that wall. Quite often you come across a wall that's actually moving a little bit or is being seen to fail, okay? So it's extending the life. I know from certainly my experience up in the UK, we've got a lot of old walls, heritage walls, and they're protected and they don't want to take them down. So this can be quite a ideal solution to actually keeping the wall and extending its life, okay? And certainly here in Australia, maybe retaining walls that come into the end of their life after maybe 40, 50 years, these are measures that could be implemented to extend that life of that retaining wall. So I'm going to give you an overview of a small case study for remedial works here in Queensland back in 2015. This was for actually Queensland Rail. A small contractor carried out the works, a company called Australian Marine and Civil. Just a little bit for your interest, this rail line is the oldest rail track in Queensland. The platform itself was built in the 1960s, so the concrete in the platform itself is reasonably hard, having had 60-odd years to harden and to mature. The works involved, it was a permanent works application and involved installing 16 of these percussion-driven earth anchors with typical design loads of up to 3 tons or 30 kilonewtons. Now, the biggest advantage of adopting this system on this particular job was that because it was a rail job, we had a very sort of short possession window of 12 hours to get in, do the works and get out. So you can imagine if you'd have adopted, say, a drilled and grouted solution, you'd have had to then revisit the job at another possession window to load test. Whereas on this particular job, because you can instantly load these anchors, we could get load straight away and move on and complete the job. So here's some images of the job. It wasn't a particularly high wall, platform wall, maybe up to 1.5 meters. And I have to say that the critical path was actually coring holes through the side of the platform to allow the installation of the anchors. And all those 16 anchors were installed over those 12 hours but was governed by actually coring through the platform wall itself. Okay, now going to share a couple of permanent slope stability applications using these anchors in Australia. Before I do, Mike mentioned about heavy rainfall events, and I have to say on the eastern seaboard of Australia, certainly in Queensland and New South Wales, and certainly northern New South Wales, we've had some significant heavy rainfall events this year, particularly at the beginning of the year, February, March time, where we just really had a lot of rainfall, intense rainfall, which caused all sorts of slope stability and retaining wall problems. And these are just a couple of images of typical outcomes. The one on the left here is a rail project, and you can see, you know, the disaster that's been caused here, and it's closed off this railway line, okay, from this slip that's happened overnight. And from one extreme, sort of commercial extreme, to even residential properties, you can see that this is somebody's house, or it is somebody's house, and you can see the slips that have happened here. And we've got to get in there and provide potentially anchoring or saw nailing solutions quite quickly to stop that from failing further. So the first project I'm going to introduce you to was a project called Mount Cotton in Queensland that was constructed in 2018. We've got, it's a main roads project here. The consultant was Cardno, and a good local contractor called Deval Constructions carried out the installation. It involves stabilizing a 150-meter length of cut slope, already cut. Mike mentioned about various retaining walls, you know, either having to take all the material out or build out and maybe a reinforced soil or bruise of mass gravity. In this case, we've already got this 50-degree slope. After the event, the engineer realized that it needed stability measures. So we're coming in and we're putting anchors or we're putting nails in there to stabilize it. So up to 4 meters in height, and as I say, 50-degree slope angle. The works involved installing some 200 of the percussion-driven earth anchors, typical design or working loads between 3 to maybe 6 tons, so 60 kilonewtons. The thing I want to sort of highlight here is this was very much a value engineering approach, and the engineer and the various stakeholders were quite happy to detail and to come up with a solution of a design life of 60 plus years. Quite often in Australia here, particularly structures, we're looking for a 100-year design life. But on this particular occasion, we've gone with a soft engineering and a hard engineering phase solution, but with a 60 plus year design life expectancy. Here's just some typical sections of the anchors being detailed, certainly around, and a couple of the embankments. There were culverts in there, so we had to carefully space the anchors around the current culverts that were in there. And then that's an elevation. The red dots are actually the spacing of the anchor solution. I think typically 1.5 by 1.5 meter centers. Let's have a look at a few photos of the installation. On the left here, you can see the anchors already having been installed. This photo image in the middle here, I really like, because the contractor came up with a very nice way of spacing the mesh, because this is going to be shotcreted or sprayed with concrete afterwards. And he's come up with a very nice method of a small paving slab, not very big, and drilled a hole through the paving slab. And that acts as a spacer and something to spread the load on the slope for the mesh, and then the shotcreting to happen afterwards. So it's quite a clever, I thought, clever way of actually detailing the spacing of the mesh away from the slope. And there we have some images of the finished job. The top, a hard concrete solution, and at the bottom, there's actually some hydroseeding measures gone on there with some vegetation expected to take shape in the future. But you can see what that embankment's doing, very much supporting a road and a highway at the top there. Another permanent works project in Queensland, and this was up at a place called Noosa, which is on the Sunshine Coast. Key stakeholders on this particular job, the council, the local Noosa Regional Council, a consultant called Geotechnical. We're stabilizing 30-meter length of existing slope up to 6 meters in height, about 50-degree angle of repose. This time we're not going that deep with the anchors, we're addressing shallow slips. So these anchors, 70 plus of them, you can see the small loads, relatively small loads, 1.5 tons, 15 kilonewtons. And we're just driving them maybe 1.5 meters, 2 meters into the embankment to deal with shallow slips and to hold the erosion mat into position. Very much a value engineering approach again with the 60-year design life. And there's some images of the erosion matting being placed and the anchors being tensioned up. Remember that we're only addressing shallow slips here and also a decent anchoring system to hold that erosion mat in place. There's erosion control there, and then there's also strength and tension in that mat to spread loads or stress loads between the anchor heads. Difficult to access job, and it was nice to revisit it maybe 6 months afterwards. Little drone shots there of, you can see the slope starting to vegetate, and that vegetation, very important part of, helping stabilize that very steep embankment with the anchors. So the encouragement of vegetation, very important. Right, I'm going to sort of wind up now with just some one-page photos of typical jobs that I've been involved in, not full case studies, but just to give you an appreciation of just the sheer number of applications where you can potentially use this type of anchoring system. This first one is in far north Queensland here in Australia, very prone to cyclone weather. And actually this was a temporary bridge. This is the new temporary bridge that's being constructed, but the first temporary bridge was washed away in a cyclone. Very remote area, some 30 or 40 kilometers from the nearest town. So very hard to get concrete, very hard to maybe mobilize, complex piling rigs, etc. And the engineer came up with the idea of holding this bridge down, the abutments down, using raked percussion-driven earth anchors, okay? Quite large loads. Remember, I think around 10 tons on this one. But those anchors being raked to deal with various uplift and horizontal forces that a very fast-flowing river cyclone event can, put on that bridge. But the remoteness of the job and the idea that these anchors went in very quickly was very much appreciated by the contractor on that project. This was a job down in a place called Newcastle in New South Wales. The engineer on this was ACOM. It's a shared access retaining wall across a railway line again, and it is anchor systems. The engineer wanted some additional holding back force, and I can honestly say I was on site for this job. All 7 anchor systems were installed in the morning, and load quantified. And then that allowed the contractor just to go and do the backfill in the afternoon. So very quick system to install and then to carry on with the works. And I actually quite like this top termination plate that the engineers designed to deal with the loadings. Coming into some slightly different applications now, very much holding down. I believe this was maybe one of the first, if not the first, floating solar panel farms in Australia. I think maybe in Indonesia, this may be taking off and you're looking at solar panel farms on water and certainly on dry land. But in this case, we've installed percussion-driven earth anchors around the outside of this pond. It's actually a horrible sewage treatment plant, so it wasn't very much fun putting actually the anchors in the water here, which we had to do as well. But so there were anchors put in the water and also all the way around the outside to hold down that or provide a holding down method for wind and also flooding events as well. And you can just see the anchors being loaded here with a simple load cell. Keeping on the renewable energy theme here, This is a dryland situation now. Again, far north Queensland, where we do experience some quite, extreme weather, certainly from winds and rainfall events. But what we had up here is a situation where when this solar panel farm was installed, we couldn't actually, or the contractor couldn't actually get the piles deep enough for the engineer to sign off on it. So what we had to do was come up with a retrofit solution. So in other words, add the anchors in afterwards as a holding down measure. Okay. We actually on this job used 2 different size anchor heads, so that when we got into the harder ground, we went with the smaller head. And actually when we got into softer grounds, if we experienced them, we would go with a bigger head to give you those tie back loads. Typically, I think they were up to 2 tons, so they weren't very large, 20 kilonewtons, I think. And then finally, I wanted to put this one in. If any of you have ever had any experience with drains, with vertical drains, relief drains for relieving pore water pressures, this is a horizontal version of it, if you like. And what the anchor head is then used for is it's actually sacrificial. It's used to pull, so you drive the anchor into the soil and it pulls this type of drain, fin drain behind it. And that forces a drainage path and also arguably gives pore water pressure relief. Okay, so it's a bit like a horizontal wick drain. If you have any experience with vertical wick drains and foundations, relieving pore water pressures, this is just a horizontal version of it. And quite often when you're detailing this type of system, the ground is quite saturated and quite soft anyway. So these actually do go in quite easily when specified and adopted. This was a job down in South Australia for a rail over. You can see it's a rail line, of course, for the bridge abutments to alleviate the water pressures and behind the walls. Okay, so that's effectively the end of my presentation. So I'm going to give you just a very brief summary of what we've discussed, really about the key benefits of this system. It is simple and an effective concept. It's not always going to be the answer to your engineering problems. As I mentioned earlier, they're not rock anchors. Whilst you can get them into some pretty hard materials, I've certainly got them into weathered mudstones before. They're not a rock anchor, so it's got to be displaceable soils. So they're lightweight, fast and easy to install, and very importantly, that immediate load verification. Typical holding capacities, ultimate loads now, maybe that 20 tons. Okay, so quite a large range, or quite a reasonable loading range to solve your engineering problems with. Can be used for temporary and permanent works, and that no mess, maybe environmental benefit as well. Imagine if you were putting an anchoring or nailing system adjacent to a watercourse, and you don't want to contaminate that watercourse. This is a dry system, so you're not going to messy grouts, maybe potentially getting into a nice river or a watercourse situation. So arguably a low environmental impact solution. Thank you very much for listening. I hope you enjoyed my presentation.
No, thanks very much, Dave. That was, I'll put the video on. Here we go. Maybe coming up. That was very interesting. I must say, there was so much information that you presented there. There was a lot to take in. So far on the Q&A, I have one question, but actually it's a very good one. And I'll just read this one to you. It's from Milind Meher. Is there any reduction factor considered in the proof load based on spacing of anchors? That's quite a good question, that.
Interesting. That's a new one on me. Spacing of anchors, a reduction on proof load. So in other words, are you saying that if you close up the spacings, you don't need to have such a high proof load? Is that the question being asked?
Well, I guess the main target of the question is if the anchors become closer together, the zone of resistance may start to interfere from anchor to anchor.
Yeah. You know, generally as a rule of thumb, I would say you would not space them any closer than 1 meter. Okay. And it's more for probably mechanical damage than anything else, particularly if you're going very deep into a soil. Okay. Maybe in 8, 9, 10 meters or something like this. You're going to get, there is an opportunity or chance of them wandering. Okay. So a meter is a good. There's also discussion, Mike, on actually if you do close them up, that they actually don't interfere. The cones don't interfere, and they become to act like a raft, like you were if you were designing a raft footing. I mean, there would have to be a bit more engineering analysis and research done on that, but there is argument that actually there isn't any cone interference, but they actually start to act as a raft type of solution. Yeah.
Yeah, no, that I can certainly see some sense in that. Yeah, yeah, I think certainly I could see that being a concern sometimes. But okay, so that's the only question we have on the Q&A. But I've certainly written down a few things. I don't know if anybody would like to put their hand up and ask a question live to Dave at the moment, or whether Phil, maybe you have a question you'd like to ask. So I've written a few things down here which interested me, and I'll come back to some of those. But would anyone else like to come on and ask a question to Dave? Okay, well, let me start off then with a couple of things which, I mean, I'm just wondering, I don't know how many different sizes of the anchor head you have, but how easy is it to judge the size of the anchor head you need compared to the load required and the ground conditions you're working in? Because that clearly is an important skill to avoid either getting failures or getting too much resistance more than you need. So I guess you must have some good clues about that.
Yeah, I do, Mike. I mean, you know, I have developed my own Tasagi and Skempton spreadsheets, you know, for soil, different, you know, shear strength parameters, and for different size heads. You know, you do, I'll be honest, having had so many years doing this type of work, so you become a little bit of a whisperer, I'll be honest, where you do get a good feel. Even if you go to a job and you see an anchor being driven, and you even just the sound of the driving of it, you get an idea of how hard that ground's going to be and what sort of loads you're going to get from it. Yeah. But you do put bearing stress theory and behind this, and you can, I know there are certain companies that got their own software that you can, you know, sign up to, and that will quite accurately give you the load from their anchor head, you know, their size of anchor head in the different soil types. Okay. So the inputs, the variables, remember, are the soil type, your shear strength parameters. Yeah. Maybe if it's a friction soil, that overburden load starts to come into play a little bit as well. You know, the weight of the soil on top of the anchor head itself. So, you know, you asked how many different sizes. Well, you know, the biggest I've seen is probably 700 or 800 mil in size. So, you know, nearly getting up to that meter size. So that's quite a big anchor head. And then the smallest, maybe simply 50 or 100 mil in size, you know. So it very much will depend on that soil that you're driving it into. I know in Brisbane River, we have a thing called a Holocene layer, which is a very weak clay. It's a bit like a black toothpaste. That's probably a good description of it. And I've punched the biggest heads into that, and I've punched the smallest heads into that. And in the smallest heads, they just pull straight through. And even in the biggest heads, I might only get maybe a couple of tons because the shear strength, they're so weak. Yeah. So it really has, that shear strength of the soil has a bearing on, you know, what size head you adopt and what sort of load you will get out of that anchor system. Yeah.
Interesting. Am I right that actually that sometimes they use for recreational purposes, like holding tents? You know, if you yeah. little anchors.
Yeah, absolutely. you know, I never, every time I go and do a job with this type of system, I sit back and I see them driven and I see them loaded up, and I'm always in anticipation whether they're going to take some load, you know. And very rarely do they disappoint. But even the smallest ones, and I could give you a small anchor and you could go and drive it to 500 or 600 mil or whatever it is, and you try and pull that out of the ground, say in sand. And I've been on project sites with some of the biggest, you know, contractors coming along, trying to pull them out of the ground. And I'm basically, I'm betting them. I'm saying, if you can get it out of the ground, I'll buy you a beer, you know.
Oof.
And, you know,
safe bet, yeah.
It is.
Nice. Right, lovely. Okay, got a couple of requests for live questions. I think first of all, I think Phil, would you like to unmute and ask a question?
Yep, sure. Thanks for your presentation, Dave. I'm glad to say that see that this system is you know, is still really being used. I have used it myself many years ago, early 2000 in New Zealand, and it was very successful. Very rapid and portable system. And I guess with your slides about significant weather in Australia, I mean, this kind of slip remediation is probably going to be something that we're going to be seeing a lot more of. We seem to be getting more extreme events around the world, and so I can see this really taking off. What's the process for using it in Indonesia? Have you got a branch here, or how would it work if we saw applications here?
I'm very interested in seeing it used around the world. I've certainly had experience of using it in some of the Asian countries, particularly India and actually even in the Maldives of all places. In the Maldives, you got ideal, believe it or not, soil conditions. There's sand, and they hold down very well, you know. Look, I'm very keen to help, you know, get a project going maybe in Indonesia with this system if they're not there already, and nobody's experienced them. What I would say to you is it isn't a system that you just buy and not expect that you can simply do it yourself. You know, you've got to go to somebody that's probably had an element of experience of using it and whether it can be used or not, you know. So yeah, have a look at your geotech in Indonesia, and certainly with the greatest respect, I'm sure you get weather events similar, very similar, if not worse, to what we have here in Australia, and that's one element. But maybe have a look at your geology. And you know, in Australia here, I can categorically tell you, you can't use this system everywhere. You know, basically we live on a great big piece of rock here. But there are applications for it, you know. If it's a road, if it's a highway, there are displaceable soils where you can use it. But we do have also a lot of rock here in Australia where you have to go to another type of solution, like a drilled and grouted or a self-drilling system or whatever, that will solve your problem for you. So my first thing with Indonesia is I'd say have a look carefully at, you know, okay, the application, what sort of loads do you need from it? What is your geology like? What is your geotech information telling you? Yeah.
Yep. Thank you.
Thanks very much for that response, Dave. Actually, we also have a question from our MC, from Malvin. Malvin, would you like to ask your question?
Yeah, thanks, Mr. Michael. Hello, Mr. Dave. I would like to ask that, can this anchor be used for mitigate or prevent landslides, especially in steep mountains? Is it possible?
Absolutely. You've got to look at the modes of failure. First of all, you know, if you're looking at a slope and, you know, you're doing an assessment on it, you might do some stability analysis. You may have had some geotech done. You may be concerned that there's going to be a failure in this slope, yeah? You've got to look at what type of failure potentially can happen. You know, is it going to be a landslide? Is it going to be a deep-seated circular slip? Is it going to maybe be a shallow slip? Because with this type of system, if you model it, you've got to drive these anchors far enough past a potential slip plane. Okay, if that makes sense. As you also have to do with drilled and grouted solutions. Okay, so model your slope. The more information you have on the geometry and the geotech, the more chance you can then work out whether you've got a potential factor of safety against failure or a very low factor of safety against failure. And then you can, if the soil will allow it, you can look to introduce this type of anchoring system to increase that factor of safety against failure. Yeah.
Okay. Another one I would like to ask: can this be used for liquefied soils? Is it possible to?
I've never got involved in using this for liquefaction, you know, resolving a situation of that nature. No. You have lots of problems like this in Indonesia?
For landslides, there's quite a few, but for liquefaction, like it's only just for case studies like that.
Yeah. Yeah. You know, this gets into geotechnical engineering and, you know, an experienced geotechnical engineer to really look at that slope and to look at the potential failure of that slope and what measures can be put in place to stop that from failing. Yeah.
Okay. Thank you, Mr. Dave. That's all from me.
Okay, thanks. Thanks very much for those responses, Dave. I mean, the liquefaction question is certainly interesting. Of course, we had the terrible earthquake that affected Palu a few years ago, and the liquefaction was horrific. To be honest, I don't think there are many things that could have resisted what happened there.
No.
But it's certainly interesting thought. I think we have another question on Q&A, which Ching Sheng Chen says thanks. There you are. There's a very nice message for you there, Dave. Thanks very much from Ching. So that's nice to hear.
My pleasure.
And actually, I just have one more little question on my own list, which I was slightly curious about on a slightly technical issue. Was so when you tension the anchor after you've driven it in, you take out the driving rod, and then you get hold of the cable and pull. I'm just wondering, typically, I mean, how much distance is involved in that tensioning? How much are you moving things?
Good question, right? Tried to explain it a little bit in my presentation, but it's a good rule of thumb. Certainly, we're trying to understand the load locking procedure. In other words, that anchor flipping over into the soil, and then it starts to take the load, yeah? Okay, so that's where you're going to get most of your extension, all right, most of your tension. Now, there is a pretty good rule of thumb, which I would say 95% of the time is pretty accurate. And that is in cohesive, let's start with cohesive soils, which are softer, yeah? It will take somewhere between 1 to 3 anchor lengths to turn in the soil, that initial extension. So in other words, if your anchor is 100 mil long, okay, if it's a cohesive soil, you're more likely probably to take 2 to 3 times. So that's 200 to 300 mil extension, okay, before you then start to take load. Okay, well, then you don't get so much extension anymore. With friction soils, that's less. It might be just 1 anchor head. So that'd be 100 mil, if it's a 100 mil anchor, yeah?
Yep.
Now, that's pretty accurate in my experience of trying to understand how much extension or how much pullback is going to happen. And you do need to understand that, because if you're designing these anchors for slope stability, you need to understand exactly where you want that head ending up in the soil. It has to be a certain distance past that potential slip plane. Okay, so in other words, you've got to overdrive and allow for that extension back, yeah? But most of that extension, Mike, is in the turning of the anchor, the flipping of the anchor to become a dead man, yeah? That initial extension where you don't get much load, but it's just what they call load lock, yeah?
No, that certainly makes sense. I think, yeah, you can understand why that would be the case. So, yeah, very interesting. Now we have no further questions, and some of the things I'm interested in, I've now asked, and I don't know if anybody else has a last question before we let Dave go. I mean, it's getting a wee bit late where you are. No, not. Oh, it is a bit. No, not too bad. Not too bad.
No, it's not too bad.
Yeah. But I think if nothing else, nothing else coming up in the Q&A, well, I would just like to thank you again for staying up this evening to present this to the IC Local Association here in Jakarta. I mean, I'd have thought we have a lot of soil types, you know, because we have deep residual soils. They're often being exposed in very steep cuttings, and of course, the hope is they'll stay up forever, but that might be the case. So I don't know. It seems to me that we could have some conditions that could be extremely suitable for this kind of earth-based anchorage system. And yeah, I'm sure it's something to be looked at. Whether or not these sorts of systems are already available, I really don't know. But anyhow, I thank you again, Dave, very much for this. And we would just ask if we could have PDF copy of your slides, if that's okay, that we could circulate to the people who've been listening in tonight, because it's very nice to have a record. That's very nice. And I think on my side, I'd just like to say one more time, thank you, and hopefully catch up with you before too long, maybe down in your part of the world if I get down there again. And yeah, enjoy what's left of your evening, and shall hopefully be in touch soon.
Thanks, Michael. I've very much enjoyed presenting, and I hope you found it reasonably interesting. Yes, thank you very much again.
Very interesting. No, don't worry about that. It was very interesting indeed. No, thanks very much. And I'd like to hand back now to Phil, just to bring the evening almost to an end, and then he'll hand back to our MC Malvin after that. Okay, Phil, hand back to you.
Thanks, Mike. And just once again, thanks very much, Dave. Making the time to come and talk to us. I think this system has got lots of potential here. I mean, just to back up what Mike was saying, quite often we have very difficult access locations, either temporary or permanent works. And, this is a highly portable system, very versatile. And I think tonight already you got people thinking about, potential applications for this system. So yeah, hopefully we'll see more of it. Certainly the systems I've been looking at it recently have been more the traditional soil nail type applications. So obviously the beauty of this kind of anchor is you load test every single one. You have to do that to install it, and as a geotechnical engineer, that's a huge benefit. So yeah, I'll certainly be looking for opportunities to hopefully talk to you guys. And so on behalf of us, thank you very much once again, and to all the 50 odd participants who attended, thank you. And it's good to see you on the call again. And we'll look forward to seeing you next month, hopefully in our normal location at the EP. So thank you. Thanks everyone. And just hand over back to Malvin to close. Thank you.
Okay, thank you, Dave Markham, for your excellent presentation, and thank you also to Michael Doby for guiding the session. Ladies and gentlemen, we have now reached the end of the event. Once again, thank you for your participation. We hope we can see you at the next event. Finally, good evening and stay healthy to everyone.